Okay, let's jump right into this explainer and uncover the invisible technology that literally allows machines to feel and interact with the physical world around them.
I mean, think about it. How does a robotic arm actually know exactly how hard to grip something without crushing it? Or how does a smart thermostat know that you're getting cold? To really understand how these incredible systems work, we have to look way past the mechanical parts. We got to look past the gears, the motors, the shiny metal exteriors, and ask, how do these devices actually sense their surroundings in the first place? Because without senses, they're basically just lifeless statues.
So here is our roadmap for today. Section 1, the brains of the operation. Section 2, sensors, the system senses. Section 3, analog, the continuous wave. Section 4, digital, the binary translators. And finally, Section 5, real-world applications. Let's kick things off with Section 1, the brains of the operation.
A really common brain you'll see in mechatronics is the Arduino. It's an open-source microcontroller platform. Basically, think of it as a tiny computer sitting on a single chip. It uses its programming, the code you write for it, to make real-time decisions for interactive electronics based entirely on the inputs it receives. Now, for the heavy lifting, you might step up to something like a Raspberry Pi. This gives you much higher processing power, enough to run full operating systems for really complex tasks like advanced robotics and artificial intelligence. But here is the crucial catch. Just like a human brain sitting in a jar on a desk, these super powerful processors are entirely blind and deaf on their own.
Which brings us perfectly to Section 2, sensors, the system senses. A brain is completely useless without its senses, right? Just like your biological eyes and ears, mechatronic sensors are the absolute crucial bridge between the messy physical environment and the clean, organized electronic system. They gather data on literally everything from temperature shifts to physical motion, and most importantly, they convert those physical changes into electrical signals that a computing device can actually read and understand.
Moving right along to Section 3, analog, the continuous wave.
So, analog sensors. These guys listen to the physical world in a continuous, smooth wave, and that makes them absolutely fantastic for fast, precise, real-time data. They're generally pretty simple in design and really cost-effective. However, they do have a notable weakness. Their wires can actually act a lot like antennas, picking up stray static or electrical noise from nearby clocks and devices, which is a phenomenon known as electromagnetic interference, or EMI. Let's look at some real-world focus examples here. An analog microphone, for instance, acts exactly like your own human ear. It picks up a continuous, uninterrupted stream of raw sound waves. Then you have thermocouples, which measure temperature in a very fluid, continuous way, and light-dependent resistors, which constantly react to the exact intensity of light hitting them. They absolutely thrive on that continuous, streaming input.
All right, Section 4, digital, the binary translators.
Well, if analog is a continuous wave, digital sensors handle the physical world a bit differently. They're basically like having a built-in translator right at the source. Instead of sending a continuous wave down the wire, they sample the physical data and immediately convert it into the binary language of microcontrollers, just ones and zeros. This is huge because it means they provide highly stable data with minimal signal loss, they're vastly less affected by that pesky electrical noise we just talked about, and they actually offload a lot of the initial processing work right off your main microcontroller.
To put this into perspective, think of a drone trying to stay perfectly level in midair against strong, gusting winds. It relies heavily on digital gyroscopes to measure orientation and accelerators for motion, feeding incredibly stable, rapid-fire binary data directly to its processor. Proximity sensors do this too, reliably telling a system if an object is present or not, without the data degrading as it travels along the wire. So, when you're actually designing a system, choosing between analog and digital really comes down to your specific needs. Analog is going to offer you a constant, quick, and cost-effective signal, which is perfect if you need raw, real-time data and you can manage the noise. Digital, on the other hand, gives you highly accurate, stable, and noise-free data handling, though it often comes at a slightly higher cost because of that built-in filtering.
But here is a fundamental roadblock. The physical world is inherently analog, right? But our computer brains only speak digital. So how on earth do they communicate? Well, we often need an ADC, an analog to digital converter. This subsystem steps in and acts as the ultimate translator between the two domains, converting real-world analog signals into software-friendly digital binary data.
Here is exactly how that translation flows. A continuous, sweeping analog wave enters the ADC on one side. It gets chopped up, sampled, and translated into discrete ones and zeros for the digital processor in the middle. And eventually, that processed data might even be converted back into a physical analog action on the other side. It is just a brilliant, complete, integrated loop.
Now, a major goal when designing these sensor arrays, especially when routing those super-sensitive analog waves before they even reach the ADC, is achieving a high SNR, or signal-to-noise ratio. We literally need to design the system so that the true signal we actually care about completely overpowers any background static or interference. We want crystal clear data, not environmental static.
And that leads us right into Section 5, Real-World Applications. Let's tie all of these isolated concepts together. The beautiful journey of a signal in a data-driven mechatronic system pretty much always follows these 4 steps. 1. The sensor detects a physical change in the environment. 2. The ADC translates that analog data into digital binary. 3. The microcontroller acts as the brain and processes that data using its algorithms. And 4. An actuator, like a motor or a hydraulic arm, performs a physical action based on that data.
Whether it's a smart thermostat silently tweaking your home's climate based on a simple thermocouple reading or an intricate industrial robot assembling cars on a high-speed factory line, this continuous loop of sensing, translating, and reacting is happening flawlessly thousands of times a second. It's pretty mind-blowing when you think about it.
As we wrap up this explainer, I want to leave you with a somewhat provocative thought. While you and I are limited to just 5 biological senses, the mechatronic devices surrounding you right now possess an incredible invisible array of senses. From microscopic shifts in acceleration to tiny fluctuations in magnetic fields, they are tuned into a reality we can't even perceive, and they never sleep. So what else in your room is sensing you right now? Keep asking questions and keep exploring the amazing systems all around you.